So it's my pleasure to introduce the next speaker, Professor Michel Gendreau, who is a professor of operations research at École Polytechnique de Montréal. Professor Gendreau is a well-known researcher in operations research, has received many honors, many awards. Among them, he's an Informs Fellow, was editor-in-chief of Transportation Science for a few years. And he also has, his research interests are very broad, actually. So among them, there is stochastic programming, and specifically how stochastic programming can be applied in the context of solving transportation and logistics problems. So, and today's talk is exactly on that, so on stochastic vehicle routing problems. And so, Michel, you have the floor.
Thank you, Walter. So this talk will, I would say it's going to be kind of a change of pace compared to most of the previous talks that had a pretty methodological focus. Here, we're not looking at devising a broad family of techniques or generic solution procedures. We're just tackling a specific problem. It happens to be a vehicle routing problem. So as Walter said, well, it's somehow one of, I would say, stochastic vehicle routing is in many ways one of my favorite topics, if not my favorite topic. And I often say that if I was allowed to work on only a single topic until I retire, which may come sooner than you believe, it would be some kind of stochastic vehicle routing. So this is joint work with Fabian Torres, who's a PhD student in Polytechnique, hopefully finishing his dissertation pretty soon. Let's hope this is not too stochastic. And Walter, who is the co-supervisor of Fabian. So the title is Vehicle Routing with Stochastic Supply of Crowd Vehicles and Time Windows. So let me first give you the outline of the talk. I will give you some brief introduction to the topic. I will describe more precisely the problem that we've been working on. I'll just give pointers to some previous work. And then there will be two main parts in the talk. One has to do with the modeling of the problem and the other with solution approach. And then I'll present you some computational results. And I'll finish with some concluding thoughts and future developments. So what we're talking about now is put in the context of the so-called sharing economy, where you have all those Uber and Airbnb and things like that. So in the context of freight transportation, there has been freight transportation and e-commerce, where you have now more and more businesses that are sharing both an online presence and a brick and mortar assets. So there's been the development of what has been called crowd shipping. Two companies have been at the forefront of this. Walmart, which had this idea that in-store customers could deliver goods to online customers. And this class of problem is usually called VRP with occasional drivers, and we'll come back on this later. And there is Amazon, which has launched this initiative, which is called Amazon Flex, in which a pool of flex drivers is used for deliveries. And for those who are completely unaware of Amazon Flex, you could see this as the Uber of parcel delivery. So instead of having Uber drivers moving around people, you have Amazon Flex drivers who are moving packages and other objects to Amazon customers. So we are interested in this very specific group of people, the so-called crowdsourced drivers. Something which is interesting is if you look in the literature, there seems to be some disagreement about what should be the exact definition of the crowd in this context. We will use it to refer to a person who's an independent individual who has access to his or her own vehicle and who is willing to exchange his or her time to perform deliveries for monetary compensation without contracting any obligation in the long term. So basically, it's very much a one-shot type of thing, a bit like Uber drivers do. Okay, I want to do some driving today. I do some deliveries today. Now, one thing which is interesting, and the reason why I'm insisting on this is because it gives you, I think, a more insightful understanding of the models that we're going to be developing, is what are the motivation of those crowd drivers. So there's been a survey by Azeker and Zirkelbach in 2020, and they found out that money makes the world go around, as they used to say in cabaret. 89% of the people who are ready to work as crowd drivers do it for the money, for the financial remuneration. And this is what motivates them. Perceived autonomy is also an important thing with 59% of the participants. Then there's the enjoyment to deliver. I'll let you guess what is this refers to exactly. Community relatedness. And one assumption was that maybe people would be motivated by skill development and maybe some environmental issues or things like that. Well, 0%. I mean, the people who are involved in those things, they don't care about those things. Basically, what drives them is the money. So what is the conclusion from this? Is that if you're going to have a successful crowd shipping platform, you need to motivate those crowdsourced drivers through compensation and try to interfere as little as possible with their activities. So autonomy is very important. It's not so much the one thing that you can act upon when you're setting up a platform, but this is the one thing that you can refrain from interfering with the way you operate your platform. Now, if we look, for example, at just a summary of some of Amazon Flex requirements, they have basic security requirements. Obviously, you should not be, I don't know, some kind of international criminal going around. They train people through some workshops on how to deliver packages. Then, very important, Flex driver must have a vehicle which is at least as large as a 4-door sedan. And the idea is that they don't want to worry about people that would have small cars and they would have to prepare I would say, adapted routes for those people. So they have this idea that they have a basic standard and everybody is operating a vehicle which is at least as big as that. Then they driver use apps to resolve shifts, which can be from 3 to 6 hours, and they get compensated at a fee which varies from $18 to $25 an hour. Now, something which is important is that the compensation is based on the estimated time of the route. So it's not the actual time that it takes to make the deliveries. So if somebody would decide to perform a route in, I would say, a very inefficient way, well, that's okay, but it's not going to get more money for that. The other way around is if somebody drives at super fast, violating all speeding regulations, well, again, this is not the trouble of Amazon Flex, because Flex drivers are responsible for their own vehicle costs. Okay, this is gas, tolls, maintenance, and I would say tickets. Now, something which is important in the problem that we're going to be looking at today is that undelivered customer packages must be returned to the fulfillment center. And this means that when we're building routes, we will account for a possible return to the depot. And basically what happens is that if there's no need to go back to the depot, well, the driver gets a free ride. He gets paid for part of the trip that he or she doesn't need to perform, but has been accounted for. So the problem that we specifically decided to focus on is that we're going to be considering a one-day delivery setting where some retailer that sells heterogeneous products of different size from a central depot. So we have a central location. You can think of this as this could be an Amazon fulfillment center. It could also be maybe a large depot or warehouse in some suburb. The products can include all kinds of goods. We don't worry so much about what they are, but some of them might be small, others might be bulky. Also, some items could be time sensitive, and then they need to be delivered within a strict time window. Some other products would require a customer signature, and then they cannot be left at some drop-off location. And also, we consider that customers' lives are not controlled by the retailer, which means that it could happen. People don't have to be there. It's better when they're there, but if they're not there, they're not there. So it might happen that some customers are not present to receive packages. But as you will see, we don't worry very much about this. Okay, in our setting, we will have two types of vehicles, so-called regular delivery vehicles that are driven by professional drivers, which we call PVs, with some given capacity. So those are delivery trucks either operated directly by the retailer or just contracted by the retailer through some 3PM or courier companies, whatever. We don't care so much. The idea is that we have access to an infinite supply of regular vehicles of capacity Q. And then we have the vehicles that are driven by our crowdsourced drivers that have a capacity at least equal to Q prime. And here we assume that Q prime is smaller than Q because when you're using your car to deliver goods, it's not like using a kind of Econoline or anything like that. One of the key motivations is that we would like to use CDs as much as possible for the delivery. So we want to push as many deliveries as possible to the CDs. However, there is one limiting factor, which is that the availability of CDs is uncertain. So we have a pool of crowd drivers that have signed to work for this retailer, but basically we don't know how many will show up on any given day. The deliveries made by regular professional drivers will incur a fixed cost and a variable cost related to distance. And I will come back later to the compensation scheme for CDs. Now, if you try to put this in the context of, I would say, mainstream stochastic vehicle routing problems, where we have usually as sources of uncertainty, demands, customers, and maybe service of travel times, this does not fit in any of those categories, because basically what we have here is uncertainty about the service, about the fleet, which is available to perform the deliveries. Okay, if we just try to go over previous work in this area, the first paper that we can think of is this paper by Archetti, Savelsberg, and Speranza, in which they were looking at VRP with occasional drivers, and this was in the context of Walmart. So they would have professional vehicles plus occasional drivers who would only visit one customer. And this would be in the context of a deterministic model. Then there were a number of other authors that have proposed what we can call static and deterministic models. So basically, those are models where the availability of drivers and all the information about request and everything is given. And then it's just a matter of trying to find the best way to, I would say, to assign the demand, to split the demand between the occasional drivers and the professional vehicles. Some models have also considered some dynamic elements with dynamic arrival of sometimes pickup, but mostly delivered tasks. So we have a couple of papers here, but those models don't consider explicit stochastic information. It's just that it's kind of an online setting, and then tasks just arrive randomly, but without any distribution or anything like that. There's been a number of stochastic models. For example, a two-stage model by Dahl, Anderson, and Christiansen that looked at ODs with fixed destination and some probability of showing up. In a sense, this, as you will see, is related to what we're going to be doing, but they were only able to deal with small instances, and they would assume unlimited capacity for the vehicles. Then a paper by, I don't know how to pronounce it, Gofska, Viana, and Pedroso, where they were looking at some kind of bi-level problem where occasional drivers were allowed to reject a task with some probability. And here again, ODs were allowed to only visit a single customer and were compensated a fixed amount. And also a paper in 2020 by Dayarian and Savelsberg, where there were dynamic aspects, both with respect to customers and occasional drivers. They were using simple scenario planning approach, so to derive results. But when they were at the routing stage of either professional drivers or occasional drivers, they would do this with taboo search. And then the capacity of professional vehicles was unlimited, but occasional drivers could only visit up to 2 customers. So fairly limited scope. And that's pretty much what has been done up to now. So what is the model that we propose? Well, we propose looking at this as a 2-stage stochastic programming model with recourse. In the first stage, we will be building routes for a subset of delivery requests that could possibly be delivered by crowd drivers if they show up. And all remaining customers would be assigned to professional vehicles. And the routes for these professional vehicles are created in the first stage. So here we are just taking care of the demand that will not be considered for crowd drivers. So basically we're partitioning the customer set into 2 subsets. A subset S that contains customers that could possibly be delivered by crowd drivers, and the remainder of customers that are delivered, that will be delivered by professional drivers, so in a very standard VRP fashion. Okay, crucial assumption here is that the availability of crowd drivers will be described by a binomial distribution. So basically, what are we saying? We're saying that we have a pool of drivers who have signed up, and we assume that each of those drivers has some probability of showing up on a given day. We also assume that those decisions are made independently. Implicitly, we're assuming independence, so that the whole thing is a binomial distribution. Okay, so the modus operandi of the system is that we assume that we're going to be making routes for the CDs, and then they will start showing up. And as they show up, we assign routes to them. And we will come back on this later. And at some point in time, well, we decide that now it's starting to be late and that we need to finalize deliveries for the day. The platform decides in some arbitrary fashion not to wait anymore for crowd drivers, but just to assign the routes that have been prepared for crowd drivers to professional drivers. So the recourse here, okay, so we have this 2-stage thing. We are building the routes in the first stage. We are observing the crowd drivers who show up. So this is the random experiment. And based on this, we decide what routes should be assigned to professional vehicles. And obviously, this comes with some penalty. Okay, so how are we going to do this? Well, before I go into those details, let me talk about compensation for crowd drivers. We will assume that crowd drivers are paid in 3 different ways. A fixed cost just for delivering something. then a variable cost, which will multiply the total distance traveled by the CDs to perform the deliveries. So we say beta less than 1. So we assume that there might be also some standard rate for the professional drivers. Professional drivers, they don't have this beta multiplier, but you can imagine that there is some other conversion that will transform distance into dollars. And then there's going to be a compensation per delivery. So for each time a delivery is made, there's going to be a compensation. And basically, we assume something similar for the professional drivers, just to have some consistency. And this leads us to the following notation for the model. So you see that I just have a pretty standard graph. I have a pool of CDs, which is the set K prime of cardinality M. I have the parameters of fixed cost for the two types of drivers, capacity for the two types of drivers. We have a penalty when we use a professional driver in the second stage. And when we are using a crowd driver, well, in fact, we have this beta less than 1 multiplier, so it's cheaper to use crowd drivers. So we denote by ZR the recourse cost of a route. Then we have a bunch of time parameters. We have the distance between vertices. And we have something which we will call notation that we'll use, CR, which is just tells us what is the sum of total variable and fixed cost of a route, including the cost per customer. And we have this little funky parameter, AIR, that just tells us if customer I is visited by route R. Then the stochastic parameter is this random vector psi that tells us, well, it's not a random vector, it's a random variable, because it just tells us what is the supply of CDs on the day that we're looking at. And we have two families of decision variables. We have binary variables for the first stage. So just telling us if a route R, which is in the set of all possible routes, is part of the optimal solution. And then we have some decision variable YR, which we will need in the second stage. So what do we do with this? Well, like many vehicle routing application, we do a set covering model. So we're just asking to minimize the sum of first stage cost, which is the cost of the initial assignment to routes to either professional drivers or crowd drivers, plus the recourse cost. And we just want all customers to be visited, and we want the number of routes performed by crowd drivers to be no larger than M, which is the size of the pool that we have. This is very easy. Now, well, the thing which is less easy is this Q of lambda in the objective function. So basically, for any given solution lambda of the model, well, we need to define the expected recourse with respect to the set of routes that are in lambda and CD routes that are in lambda. So let's call M of lambda this set. And for each route in this set, we compute the cost. We have computed the cost CR, C superscript R, is the cost of performing this route using a crowd driver. And this cost it's included in the first stage. It's included in the first stage cost. So basically the first stage cost is a lower bound. It's, I would say, optimistic lower bound. It just assumes that the crowd drivers that we need will show up for all the routes. Then what do we do? Well, we can compute some differential cost ZR, which will be incurred if we decide to use a professional driver in the second stage. Not if we decide, if we have to use a professional driver in the second stage. And you have the formula there. There's just, on the left is the cost of having a professional driver perform this route. So it's a sum of fixed cost plus total distance plus the cost WR is an aggregation of the cost for customer visits. And basically and this is multiplied by the penalty factor alpha. And what do we save by not having this route performed by a crowd driver? Well, we save the fixed cost F prime, the distance related cost beta prime dr, and WR. So basically this difference will always be positive because beta prime is less than 1 and F prime is less than capital F and alpha is greater than 1. Okay, so ZR is this incremental cost. Now, if you start looking at this problem, okay, then, well, okay, I have those routes. And then maybe I know that only half of the crowd drivers that I had planned for show up. But what is the connection between the routes within the set of routes that have been prepared for crowd drivers, this set M of lambda? What are those that will be effectively performed by crowd drivers? What are those that will be shifted to professional drivers? So we need to make some assumptions about the assignment of the routes as we proceed to the crowd drivers. And in the basic version of the model, what do? We make the assumption that the platform is greedy and selfish so that it will assign routes to CDs in such a way as to minimize its own cost. Now, we can write this up as an integer programming problem for any realization of Xi. But in reality, we don't have to get into all this trouble and look at each possible realization of Xi individually. What we need to do is simply to sort the routes in order of decreasing recourse costs. You know, those ZR that we can compute for any route? Well, we just create well, here I've written a set, but in a sense, it would be more like a list H lambda, which is a sorted list in decreasing order of the recourse cost of any route in M lambda. And when CDs will show up, we will assign them the first elements in H lambda. And if we have those differential costs computed and sorted correctly with the probabilities for the different possible realization of Xi, well, then we have the value of Q of lambda. So that's, I would say, pretty trivial. However, if we think about it, it's trivial to do it. If you give me a solution, I can look at the routes in the solution. I can compute those ZR values. I can sort them, and then I can decide which one will be used. But how am I going to integrate this in my model? It will not work. Now I'm trying to do something that requires, in order to be able to compute the solution, to properly evaluate the solution, I need the solution itself and then to put it in the process. So what do we need to do? We need to, in fact, linearize the set covering formulation. And we're going to do this by integrating the priority of each route in the solution, that is, in the formulation itself, by defining those priorities. So we will introduce additional binary variables in the model. Those will be lambda SR variables, and they just indicate that route R is assigned priority S, and priority S equals 0 will correspond to routes performed by a professional vehicle. And we just denote by CSR the expected recourse cost of route R if it is assigned priority S. And this leads to this modified set covering model. So what I have at the top is I have, for any route R that I wish to consider, I assume that I can, well, first thing, I can compute the cost C0R if it's done by a professional driver in the first stage. I can also assign a cost CSR if it's prepared for CD with priority S. So all of this can be done without too much trouble. I have the normal covering constraints for customers. And then the only tricky thing is I have this little constraint, which is that I want the sum of the lambda SRs to be less than 1. What does that mean? The proper way to read this constraint is that we cannot assign a given priority to more than one route. So there can only be one priority, one route, only one priority, two route at most, and so on. So therefore, we will not be over-optimistic in our assessment of routes. But this is made internally in the model, so the model decides by itself what the priorities for the routes will be. But since we're minimizing, we will do that in such a way that we're going to do this in a greedy fashion. So the route that will get the top priority are the routes that have the highest CRS objective factor. Well, we'll have CRS such that it's, yes, we'll have the best, no, it's tricky here. It's not the best, it's the routes for which the assignment is in fact the cheapest. Okay, now we realize that the number of columns here has grown quite a bit because now we have a number of columns that depends on the number of possible priorities. And the number of priorities depends exactly on the number of CDs that we have in our pool. And this leads to another realization, which is that if we're considering large values of psi, the probability of observing them will be very low, which means that there will be priorities for which the recourse cost would be very high. and it will not be profitable to even considering assigning those routes to crowdsourced drivers. You know, if I have 10 possible drivers that show up with some probability, well, the probability that all 10 drivers show up is very low. So the 10th route built for a crowd driver will almost surely be, well, not in the mathematical sense, but almost certainly be driven by a professional driver, and we will pay a high penalty for this. So what we can do is, if we're looking at the route R star with distance dr star, priority S star, and we know that the probability that psi is greater or equal to S star, which is the probability that the supply of drivers will be at least S star, so that this route would be driven by a crowd driver. Well, we can construct this little inequality 11. So what we have on the left-hand side is the cost of assigning the route to a professional driver in the first stage. And what we have on the right-hand side is the expected cost of assigning this route to a crowd driver, given that the priority is S star. And we just compute. So we have, in this right-hand side, we have two terms. I would say the first one is when everything goes well, and the second one is when things go badly and we need to transfer the route to a professional driver. So what is the bottom line? The bottom line is, if this relationship holds, then we should not assign route R star to a crowd driver with priority S star, period. Now we can also play a little bit, and we can compute we have a magic value P bar that comes out of nowhere. No, it doesn't come out of nowhere, but I'm skipping the developments here. And the idea is that if the probability that psi will be greater or equal to S star, if this probability is smaller than P bar, then we should not consider this route for a, I'm having trouble, for a crowd driver. Now we can look at limit conditions on P bar when the distance tends to 0 or to infinity. And this allows us to get general lower and upper bounds that are independent of the distance. And we get nice pictures for this thing. As you see, we have those limits, and we see here the threshold as distance distance goes from 0 to 500 units. So here I have the blue line as the upper bound, the red line as the lower bound. Surprisingly, things can shift, and those two bounds are always valid, but depending on the exact values of the parameters, one of them will be the upper bound, the other will be the lower bound. And here you can see the cumulative probability for priorities as, those are not really the, cumulative probability, but in the inverse sense. And you see that here, as soon as given the parameters of this distribution and of this problem, the moment you try to build 5 routes for crowd drivers, you're over the threshold. So you should not do this. So basically, if we combine all this information and we just call p minus 1 the discrete distribution, quantile distribution, inverse quantile distribution of psi, well, then I can, it's kind of a, it looks in a sense like a newsperson problem argument. So we can derive an upper bound on the number of crowd drivers in the optimal solution. Okay, how do we solve this? I see that time is running out. Well, it's we just use the, I would say, the global approach is pretty standard, is that we use column generation and branch and price. So this has a flavor of many branch and price approaches for vehicle routing with time windows. So here, negative reduced cost variables, that is columns, are found by solving repeatedly some subproblems. Each column generation subproblem is an elementary shortest path problem with resource constraints. And if we pay attention to the formulation, in fact, we should have one subproblem per type of routes in the formulation. So there should be one subproblem that will generate first stage route for professional vehicles, one subproblem that will be applied to each priority of CDs so that we can feed the model with routes of different priorities. However, one thing which is important is that this is not efficient, and in fact, the subproblem can be solved using what we call a cohesive algorithm. So here you have a standard subproblem, which is just an adaptation of what you have for, I would say, vehicle routing with time windows with just adjustments for the various things. And we use NG routes as in Baldacci. And we have nice labels that will include the current customer, the load, the reward, the time, distance, cumulative dual variables, and a set of unreachable customers. And obviously new labels are created by extending existing labels to feasible customers. So this is pretty much standard fare for vehicle routing. Now, the interesting thing is we could instead solve a single cohesive subproblem. And the reason for this is because when we're solving all those different subproblems for the different priorities, we are repeating a lot of the work, except for some of the labels. Some of the labels are identical, and we can, if we organize computations in an effective fashion, we can basically reuse a lot of the information. What happens, however, is that dominance rule, since they depend on the interaction of many elements in the label, are not the same for each of the subproblems, which means that routes with high priority at some point may become less attractive, and this will have an impact on their generation. So what we need to do is to manage label in a different way So a label is not removed unless it would have been removed in every problem, uh, in every subproblem that the set uh, okay, here I just have a typo. And basically the set of all labels produced by the cohesive single subproblem would end up containing all the labels in each individual subproblem. So here you have this in mathematical terms. If I call L of S the set of labels in subproblem S, then the union of those sets is included in the set of labels for the cohesive pricing problem. And I think I will just go further here. I have more details on the dominance rule. Okay. And this brings us to the global solution approach, which is branch and price. So it's the, we're just creating those, just applying standard branch and price procedures, starting from a restricted master problem, which is initialized with routes of professional vehicles. And we just manage the branching tree in fairly standard fashion. As much as possible, we use heuristic dynamic programming. When we encounter fractional solutions, we branch on the total number of vehicles as a primary rule. And if a solution has an integer number of vehicles, then we branch on vehicle flow. Okay, let me show you results of some computational experiments based on extended Solomon instances with 25, 50, or 100 customers. And the availability of CDs is just given by a binomial distribution with parameters P and M. And here P is just 0.05 and M is 100. So you have a pool of 100 crowd drivers that show up with probability 5%. So the first thing that we do is that we compare the stochastic model with a deterministic version just to see if it's a good idea to do a stochastic model. And I'm going to show you the results. So you've got the deterministic model and then the recourse model and the VSS. And you can see that the VSS is a significant fraction of the objective function. Then to the right, you have the value of using crowd drivers. So what you have there is you have a solution with only professional. The value is the difference when you're looking at a solution with only professional drivers. So again, it pays to use crowd drivers, get savings ranging from 13% to almost 30%. If we're looking at the algorithmic performance, this thing is able to solve small problems with 25 and 50 customers. Now we have a column generation heuristic in which what we do is we simply send to Cplex the columns that we have found by the branch and price procedure at some point and solve this using the just the IP routines of Cplex. If we compare the two subproblems, the only important column really is you have the separate pricing and then you have the cohesive pricing and you have the difference. And the difference you see just in the number of columns, there's a significant difference, but what is most amazing is the difference in time. Basically, we say between 75 and 90% of the time. And then we did some other experiments, and I'm out of time. So this is exciting. Oh, we have some, yes, we're looking at some other variants of this. And obviously looking at the dynamic version of this would be very interesting. And I'm done. Okay, so I would say just in time with just a couple of minutes for questions.
Indeed. Thank you, Michel. So we have maybe time for one or two questions. Then we go again. There is a coffee break. So,
for those who don't have as much experience as I do in academia, I just put on you the trick, which is make your talk long enough so that there is no more time for questions.
That being said, we still have maybe time for one or two questions. So are there questions from the attendees? You can either raise your hand or write it in the chat. Any questions?
I don't think, Walter, you're going to volunteer for questions.
I mean, hopefully someone else. I mean, I could always ask questions.
Okay, so we have a hand raised.
One hand raised. Yes, Healing.
Oh, hi. Thank you very much for this very interesting cloud shipping problem. So I'm just curious, is the capacity of the professional driver and cloud shipping driver actually impact the route here or the capacity is somehow reflected in the problem formulation?
I'm not sure I understand your question. You mean
because like, so thinking about cloud shipping driver, so usually they use their own vehicle, which is typically smaller than a minivan. So for example, for
the capacity has an impact. So basically when we're building routes in the first stage, when we're building routes for professional drivers, we're building routes that can have significantly more deliveries than the routes for the crowd drivers. When we transfer route for crowd drivers to professional drivers in the second stage, we don't consolidate them, okay? Because this might be a bit difficult, and also there might be time issues. Because when we're doing long routes with more deliveries for professional drivers, those may need kind of a longer portion of the day. So we make the assumption that the routes, when we transfer the routes of crowd drivers to professional drivers, we don't exploit the extra capacity. That's a pretty good point.
I see. So this model is used for like one delivery time window, like for example, like 3 hours for the unknown flux.
Oh yes, you have time windows in there, and then we need to account for the time windows in building the routes. It's clear that when you're building routes for crowd drivers, maybe if you have a customer who require early deliveries and things like that, maybe you don't want to assign them to crowd drivers.
Mm-hmm. Okay. Yeah.
So there. Okay, I'm going to be very frank. I mean, this is work that something that we've been working on for quite a while, and we've been trying to make progress, but we are not working directly with a company. And this means that there are some of the subtle points about the implementation that we don't necessarily have integrated in our model. And personally, I see this as being a bit frustrating, as any other situation where you're working on something which is, I would say, practically oriented problem without having a real immediate partner. I had students working on technician routing problems, and the industrial partner left us at some point, and we had the same problem, which is when you get to the finer details of the model and the implementation, you might be missing little fine points.
So let's stop there. If there are other questions, I would invite you to ask them in one of the breakout rooms.